Hey, welcome back. So this marks a new section that's focused on mining. So we're still talking about the blockchain, but so far all we've really talked about is the fact that there are a bunch of blocks and they're linked to one another. They're referencing, each block references the previous block, and that is true. But there's this whole side of things we haven't talked about, which is mining. We mentioned that it's a way potentially to earn Bitcoin, although it's pretty hard to do these days unless you're really rich already, but it's still an option. What we're going to talk about is what those miners are actually doing and get really into detail. We've said things so far like, oh, miners store the ledger, they relay transactions, they verify transactions.
So that's great, but what are they actually doing? What are the computers doing that is using so much energy? And why would anyone choose to do that?
Well, really quick preview, roughly of what they're doing. If we go back to this demonstration, if you didn't watch this, the last couple videos, this is just a super simple blockchain visualization, not real data. Here's a block. I'm going to change this. So Kevin sends me 0.1 Bitcoin or whatever this is, and it turns red. But I'm just going to show you with this mine button. This is not actually mining Bitcoin. This is purely a conceptual thing. But I click this button, and you'll see that this thing called nonce that we haven't talked about at all is going to change. And this hash down here is going to change. You'll see it might take a little bit. No, that wasn't actually that slow. Okay, so this changed up here. This changed down here. Let's try it one more time. And yeah, this one's taking a little longer. So what we're going to do in this section, and not just in this video, it's going to take a couple videos, is explain what the heck that was. What happened? This is a microcosm of what miners are actually doing on the Bitcoin blockchain. I don't know, thousands of times, millions of times per second.
I think it's like quintillions of times every block.
To wrap that up, there is something going on with the hash down here, something going on with this nonce that we haven't talked about at all. That's just to set us up for this section. So we'll leave it at that. There's a lot of work that these computers are doing. Why would they do this?
Because they are rewarded.
Aha. Well, we've already talked about that a lot of times, so it shouldn't be a surprise at this point. But there's a chance to make some Bitcoin. So do all miners get paid, Kevin?
Not necessarily. And it's a question of who gets paid and how often. And it comes down to a concept called proof of work.
All right.
And this is the meat of the next few videos. So the definition...
You're vegan, Kevin. Can't say meat. I'm so offended for you.
So proof of work is loose. I think I wrote this or someone else did. I don't want to take credit.
Oh, that narrows it down.
Someone wrote this.
It's either me or literally anybody else.
Yeah, or it came from the internet.
Okay.
I forgot. Proof of work is an economic measure that requires a service requester to perform some work to prevent spam. And why would we want to do this? Well, before we talk about it, let's talk about a type of proof of work that we might be familiar with, and that's CAPTCHAs. So you might have experience with filling out these not so annoying little like number and letter puzzles that would be, the reason they're here is because they're hard for a computer to solve.
Yeah, so if somebody, this is chess.com apparently, if somebody wanted to, for some reason, create 1 million chess.com accounts, they could write a bot,
or they could write a bot to ask for the forgotten password of every account on the site.
Yes, so someone wanted to just try and basically do something that automate something with code to log into the site repeatedly or attempt to log in. They would need to write code that could also, use some computer vision, look at these letters and numbers, read them or figure out what they are, parse them, it's actually become a lot easier. It used to be basically
doable
impossible.
Now. Yeah, but now it's difficult nonetheless.
Yes, so it's supposed to, at the very least, make a computer work for spamming or to get through. And captures nowadays are actually much more complicated. You've probably seen them where they involve, actually from a human's perspective, some of them are very simple. They involve just clicking something that says, I'm not a robot, or what's the other one I've seen? Clicking on like Google or on
little
street
tiles.
Signs and little tiles to identify images.
Yeah.
Things that are easy for humans but hard for computers to do. Anyway, what does this have to do with Bitcoin, Kevin?
So Bitcoin takes proof of work to the next level. Bitcoin uses a much more complicated proof of work challenge that isn't just guessing the letters and numbers on a page. It's actually solving a very difficult math problem. And why do they do that? Well, we're going to go into much greater detail over the next few chapters. What Bitcoin's trying to do is Bitcoin's trying to make it difficult for any one person or any one entity to take over the blockchain by consecutively adding their own blocks. They're trying to distribute the actual additions to the blockchain to make it neutral. because this is a distributed network. So suppose there are 10,000 miners, and suppose for whatever reason there's a bug in the system, and one of those miners doesn't have to do proof of work, doesn't have to show proof of work to add a block to the blockchain. They could just add block after block after block.
They would always be the first one.
They could ignore who they wanted in terms of which transactions they add. They could shut down the network if they felt like it. They would really get to politically take over this peer-to-peer neutral distributed network.
Right. So instead, there's this really hard math problem that levels the playing field because all 10,000 miners are doing the same thing, trying to find the right answer. One of them is going to find it first, but then the next block, it will be someone totally different. It would be highly unlikely for it to be the same person, one after another. So that's what this whole section is about. What is that math problem, that challenge they're doing over and over? But first, let's finish talking about why you would do it. It seems like a pain.
So proof of work in Bitcoin is a difficult math problem based on the current pending block. And miners compete to solve that math problem, that very difficult CAPTCHA, because the first one to solve it is awarded Bitcoin. As of 2016, it's 12.5. And we'll talk about why that incentive structure is changing over time. In 2021, the reward will be cut in half. But all you really need to consider for right now is that miners are incentivized to attempt to solve this very difficult problem in order to keep the network neutral.
Yeah, so it's not just about being the first to mine a block to have bragging rights. You can make a lot of money. I mean, even though it's not 50 Bitcoin anymore, 12.5 Bitcoin in today's prices is over $100,000 roughly. So it is worth it for for anyone really, it would be worth it if you were able to win. The problem is that it's not that easy to win. All right, welcome back. So we're continuing on with our discussion of mining and proof of work, the hard math problem that these miners are trying to solve. And in order for us to explain what they're doing, we have to introduce one other part of a block we haven't really talked about. We've skirted around it. It's called the nonce.
And caveat, you were the one who told me this meant something other than number used once.
Yeah, that's what it stands for, number used once in Bitcoin, but at least in the UK, apparently it's it
means something else.
Yeah, it's slang for a pedophile. So anyway, if you're British,
that's unfortunate.
We're not. Yeah. We didn't choose this.
It's a cryptographic term for number used once, and unfortunately, there's some overlap. So you might recognize that term from being the second row on our blockchain diagram.
And yeah, remember we changed something. We clicked that mine button,
and you'll notice that nonce changes.
And you'll also notice that somewhere on the Blockchain Explorer, where are you? There we go, nonce. So it's a little longer here, but there's some number that is in this block. We're looking at 520.091. There's a nonce there. Every block has that. So what is this and why does it matter?
Well, let's see. So back to our slides. This is what we've been looking at so far. There's actually another piece of data inside of the block that gets hashed, and that is
surprise. We just talked about it.
Surprise, surprise, a random number, and that is the nonce. So, as we replace these envelopes in this diagram, at the top left we have the fingerprint of the previous block. At the top right, now we have a random number, and that random number is actually used for the challenge.
Yes.
So, let's look closer at the actual anatomy of a block header.
First, we have to get something out of the way. We've been lying to you a little bit.
We're sorry.
We've been saying that when a block is mined or solidified, the entire thing is hashed. All the transactions are hashed, plus the time, the previous header or the previous hash from the previous block. All that's hashed together. It's technicnically slightly different. How is it different?
Now, why is that? It's because the way that SHA-256 works. So it's much faster to hash something tiny than hash something bigger. So what we're actually doing here is we're actually including a hash of the transactions in the block. We just take the fingerprint of the transactions, and the output is just a 256-bit string, which is showed here as 64 characters on the bottom right. And then we include those 64 characters in the header. Okay. And the header is just these 6 pieces of data. The 3 parts that are most important to our learning in this course are the ones that are highlighted. We're leaving out the other 3. We'll go into a little bit more detail about difficulty, but it really comes down to these bottom right 3.
Okay, so to reiterate what Kevin just said, what is happening is that when we have, let's say, 2,500, 2,600 transactions in a block, rather than hashing 2,500-ish transactions together plus the hash of the previous block to get the fingerprint for this block, that takes some time. Instead, we do that once. We take all the hash or all the transactions in the block, we fingerprint them, then we add that to the header, which is what you see right here. We're doing it in the bottom right of the header. We're just displaying it like this. There's no position. It's just data. But we're doing the bottom right.
Yeah.
So then we hash this together to get a faster fingerprint.
And cryptographically, that's just as good as what's below it. Technically, it's a little less secure, but because the SHA fingerprint is so unpredictable and so hard to steer a result out of it, we're completely satisfied with just compressing the entire block of transactions, the entire list of transactions into one fingerprint, and then including that fingerprint in the header. For our analogies and for the course of mining, you don't really have to think hard about it. You don't really have to consider it as just the hash of the header, but we're telling you here just for completeness sake that when these miners are hashing a block, they're only hashing these 6 little pieces of data. It's only, I think, 768 bits, less than a kilobyte.
Okay, so now we get to nonce after that little tangent. So what we're showing here is simplified, but we're using emoji. So this is the previous block's fingerprint. This is the fingerprint of the current block. And it should be the same every time we run this, except there's going to be this random number, the nonce, that we're going to introduce. And so remember, Moby Dick, you change one lowercase l to an uppercase L, totally different output. Well, in this case, we're changing one random number, whether we're changing it from 45 to 46 or from 45 to 7,100 and blah, blah, blah. It doesn't matter. You change it, we get a different output. So when we use emoji,
we get 45, we get a CD or whatever that thing is called. 46, we get a heart. 47, we get a mosque. 48, we get pancakes. Gosh, those look good. 49, we get a saxophone.
What did you
50,
just say?
we get, is that a lotus?
I don't know. I
think that's
so.
a lotus.
It's a flower. At the very least,
It's
I
a
can tell you
flower.
it's a flower. Are we done
51,
yet?
we get, yeah, I think this is the last one.
Okay, so the point is, everything else stays the same. The previous hash from the previous block is the same. The transactions don't change. This one number changes, and the output hash is entirely different. We go from pancakes to
Saxophone,
diamond
lotus, diamond ring.
So, what does that have to do with mining? Why would you ever change this?
Well, it comes back to the challenge. And the challenge, here it is. We're finally telling you what the actual thing is.
Well,
sort of. We're getting closer. The challenge is to repeatedly hash the current block and a random number, the nonce, until you have a fingerprint that satisfies a special property.
Okay.
Spoiler, that special property is that the fingerprint should be lower than a certain number.
So, remember, a fingerprint looks something like this. Imagine, this is not the case, but imagine that you had to keep fingerprinting it with a different random number until you got a palindrome for your fingerprint, meaning that it was the same forwards and backwards. Or until, I don't know, what letters do we have here?
Until you had 1, 2, 3, 4, 5, 6, 7, 8, 9 in a row.
Sure.
Yeah.
So basically keep changing that random number over and over and over, plus keep everything else the same. Change that random number, fingerprint it until you meet some condition. That's the challenge. Now the challenge itself, Kevin already mentioned briefly. We're not going to go into that until the next video or two. But what we will do is kind of do our own version using emoji.
Yeah. And if this all sounds ridiculous, it's because it is. In the same way that filling out a CAPTCHA is completely pointless. So guessing a random number to produce an output hash that has some special property is completely pointless as of the Bitcoin blockchain. There are other cryptocurrencies that attempt to iterate on this, but for the Bitcoin world and for the Ethereum world, this is really an exercise in futility. There's no point that we're doing this other than to slow people down.
What we're going to do with emoji is, instead of fingerprints being these long strings of numbers and letters, we're going to work with emoji and continue to change the nonce, the random number, until our emoji is yellow. Okay, so we try it.
So let's pretend that our previous fingerprint was a valid emoji.
It has to be yellow.
The challenge was get a yellow emoji, and we got a tennis ball. So that was a valid block with a valid random number. Now, when we plug in the tennis ball, we plug in our current transactions, and we plug in 53, we have Harambe.
Rest
in peace.
It's a gorilla.
Now we go 54.
So we tried changing the nonce.
We get cherries.
That's not the output we want.
All right, 55, martini. 56, peanuts. I like that one. 57, surfer.
And finally,
58. Oh, my word.
A lemon. That's
it's
yellow.
a lemon. That's yellow. There's some green on it, but we're considering this a valid output
it just has
fingerprint.
to be majority yellow.
Yeah. So what we just did is we just guessed a bunch of random numbers until hit next slide.
Right. Oh,
That's a good effect right there. I worked very hard on that. So we just guessed a bunch of random numbers until we got an emoji that met our property. Now, again, I'm going to keep reminding you, this is completely pointless. There is no reason other than just slowing down computers. But the net result is that it makes it such that we only add a new block every 10 minutes. And we'll show you really the math in Bitcoin. But for now, we're going to switch over to more of our blockchain diagram where we see a few sequential blocks. So here's the old version where we don't have any particular property of each emoji. Now we have the rock on, we have the little baby chick, and then we have the fingerprint of the previous block right there, and then we got the little happy sun, and that's produced with 12 and 63.
Yeah, so these, first we should mention that there's many yellow emojis. So we're not only looking for the chick or the sun. It could be the tennis ball. It could be the
banana.
Sure.
Could be any one of the smiley faces.
Oh yeah, there we go. They're like all yellow. So these computers keep going over and over and over until they find a valid output, but there's not only one. And we'll see exactly what they're doing in the coming videos. So returning to the Blockchain Explorer, first you'll notice the nonce down here is much larger than what we have, 63 or 12 or something. These are much larger numbers. So the amount of work that goes, there's a lot of guessing that goes into all of this. These computers are basically continuously guessing super, super fast over and over and over.
So, and if you look at the hash in the previous block and the next block, you'll see that they all start with a bunch of zeros. And in the same way that our decimal system works, smaller numbers, if you pad them out with zeros, will have a bunch of leading zeros. For example, the number 100, if we're padding it to 3 characters, doesn't have any zeros. But if we take the number 9, it's actually 009. Smaller number, more zeros ahead of it. Right here, we have a bunch of leading zeros, and that's because all of these hashes share the property of being smaller than what's called the target.
Okay, you're scaring everyone, Kevin.
I'm sorry.
This is what we're going to talk about in the next couple of videos. But instead of finding a yellow emoji, this nonce is continuously changed until we find a hash for this block that has a certain number of leading zeros. We'll leave it at that. All right, we'll explain more later. All right, welcome back. So now we're going to go into detail of the actual challenge that these miners are doing. It's not finding a yellow emoji. It involves satisfying the requirements of something called Hashcash.
Yeah, Hashcash is the proof of work challenge that Bitcoin uses in the same way that a CAPTCHA is the proof of work challenge that a website would use.
Okay, so first, going back to our yellow emoji example, we have this slide here to show you these are the first, these are 30 nonces?
Yes. Yeah, let's pretend that we have a block, we have a bunch of transactions, and we have a previous fingerprint. Let's suppose we plug in 0, we get a crab. We plug in 1, we get an alien. Plug in 2, we get grapes, so on and so forth. This is a chart of those valid nonces, or of the output emoji of a given nonce.
Right.
We're showing this because we want to demonstrate that there are more than one correct answer. There is more than one correct answer.
Yes.
So, voila. 3, 8, 11, 16, 17, 27, all those nonces produce yellow emoji in the same way that there are many more than one individual fingerprint that are smaller than the target, air quotes. There are many emoji and many valid emoji that meet our our challenge requirement in emoji coin or whatever we're calling it.
Okay, so you're saying that there's more than one correct answer.
Yeah, there's lots of right answers.
So what is the actual challenge, though, when it's not yellow emoji? What are we talking about with Bitcoin and Hashcash?
So on the next slide, we have Hashcash. This is really what it comes down to. And we'll talk about how target is calculated. But Hashcash is about hashing the header. So these 6 pieces of data, 768 bits, and changing the nonce until you get a value that is less than the target. And the target is a number in the same way that all of these other values are numbers.
So revisiting the Blockchain Explorer, imagine hashing together, again, don't worry about exactly what pieces of data, but just say hashing this data together with this nonce constantly changing, whether it's being picked randomly or 1 is being added to it over and over ad infinitum until we hit a resulting hash, the fingerprint, And in this case, you can see it starts with a ton of zeros. That means that it's less than the target number. And let's just say that our target number, how many, I'm not going to count these zeros, but let's just say
that's a lot of zeros.
What is that, like 15 zeros, maybe 20?
Give or take.
I don't know. I'm really bad at counting like that. But whatever it is, it had to be less than some number. And in this case, it is.
And remember, if you were to just plug these exact values in on your computer, you would get exactly the same fingerprint. So in the same way that it's easy for a website to verify that a password is correct, it's very easy to verify the correctness of an answer. You, with your cell phone, you with, honestly, an old calculator, could verify the correctness of this proof of work answer with just a few calculations.
Okay, and one thing I wanted to add, look, here is what a average fingerprint looks like. They don't start with a bunch of zeros. They can, but this is what a typical one looks like. Just a bunch of, maybe a couple zeros somewhere throughout the entire length of the thing. Now imagine having to do this over and over and over just to get 1 0 at the beginning, let alone 10 or however many this is. It's a lot of guessing.
So an analogy that I heard that I really liked was, imagine that this hash right here is actually the output of 256 coin flips. So the output right here, these 64 characters, are actually just a representation of 256 binary bits, 256 zeros or ones. And let's say we call a head a 0 and a tail a 1. So what Hashcash is about is, Hashcash says, I want you to flip a coin 256 times. And I want the first, what is that? Let's say those are 20 zeros. I want the first 80 flips to be heads. Now, how many sequences of 256 coin flips do you think you would have to attempt to get 80 heads in a row, if that's 20 zeros?
Right.
So it's extremely rare, and that's why all of these computers have to guess a lot of random numbers. Each random number is basically a way of attempting a new sequence of 256 coin flips. And when you do luck out and find a random number that gives you a sequence of coin flips that is the first, 20 characters, the first 80 flips are all heads, you have found proof of work, and you get a Bitcoin. You get 12.5 Bitcoin.
So just to reiterate, Hashcash involves using SHA-256 and trying it over and over and over on the block header, which includes things like the version of the Bitcoin protocol, the timestamp, and then also the hash of the previous block, the hash of all the transactions in this current block, and most importantly for now, the nonce, this random number that changes, or that you attempt to change over and over and over until you find an output that is less than a target. And what that means is that you're going to have a ton of zeros at the beginning. Exactly what that target is, changes, and how it's calculated we'll go into later. But just think of that now as the goal. Instead of a yellow emoji, we're continually hashing things with a changing nonce until we find a really small number that starts with a bunch of zeros. Alrighty, welcome back. So we're still talking about Hashcash. Now what we're going to do is just walk through a little visualization of what it could look like.
More analogies, just because this is quite conceptually difficult to wrap your head around.
So what we have here is a number line. And let's say that it goes from 0 to 2 to the 256 minus 1.
Yeah. Next slide, I actually show that number. It's pretty big.
And why does it go up to that number?
So when you have 256 bits, you can represent a number between 0 and 2 to the 256 minus 1. In the same way, a smaller example is easier to understand. If you have 4 bits, you can represent any number between 0 and 2 to the 4th power minus 1. So what's 2 to the 4th power?
2 times 2 times 2 times 2. What is that, 16?
Minus 1?
15.
Which you might recognize that number from hexadecimal. So this number right here is 2 to the 256 minus 1. It's gargantuan. It's I don't even know where to start how to say that number.
But this is the largest output that we could get from SHA-256.
Yeah, this would be the biggest fingerprint. And if you were to actually land it on the biggest fingerprint, it would actually look like a bunch of Fs.
Right.
Would be the fingerprint.
I
wonder what that'll sound like in the mic.
Think that's gonna...
So I think someone should get a reward if they ever get that. In all likelihood, it's never happened and probably never will.
Okay, so this is the range of all the possible values for a fingerprint, an output of SHA-256. Now remember that Hashcash basically the goal is change the random number until you get a value, an output of your fingerprint that is less than some target. Now, on here we have this target. This looks like it'd be pretty easy. I mean, what? It would take you a couple of attempts.
Yeah, let's say that's like 1/6 of the way. It would mean on average it would take you 6 guesses. Yeah. This is way. I mean,
we wouldn't even be able
scale.
to see. It would be a millionth of a pixel on this screen. I mean,
less. Yeah,
it would be crazy. It would be impossible to see. We'd be zooming in forever to show you the line. But imagine it's right here, and you're trying to guess a number to fit in between this white line and a red line.
Yeah, and we've distracted you here. This slide actually introduces a new piece of terminology, and I guess we've mentioned it before, but we mentioned finally how target is calculated. Sort of. It's based on difficulty. So next slide. Difficulty is a setting determined by the network, and we'll talk about how the network determines it, that scales the target in order to control the rate at which Bitcoin is minted.
Okay.
And what's that mean?
Okay, so we've talked about how the goal is to have blocks mined about every 10 minutes or so, right?
Yeah.
And what happens is that all these miners are trying to do this hard math problem, and that statistically, the more miners we have, the faster they'll be able to solve it.
Yeah, and when we say this statistically, that just means that so many people are making so many random guesses that by the law of large numbers, this actually just tends to work out to be 10 minutes every time.
Right.
It's possible that somebody guesses it right on their first try, and it could happen someday. It's just very, 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 very unlikely.
Yes. Anyway, so depending on the number of miners that are on the network at a given time, the network changes the difficulty, because if there are more miners, then we're going to make it harder. If there's 10,000 miners trying to guess the number over and over and over, it will take less time unless we make it harder. If there are fewer miners, there's only 10 of them, which this is an exaggerated example, but if there's only 10 on the network, then we're going to make the difficulty much easier so that it doesn't take decades.
Boom. So number line, next slide. Illustrated. So if we had 4 miners, we would have a lower difficulty and a higher target than if we had 8. So let's say the number of miners doubled. What we would actually do is we would double the difficulty. And that would actually make the target smaller. And that would mean that on average, the network as a whole needs to make more guesses to find a fingerprint that is lower than that target.
Okay. So we've established that.
Now we got the happy robot and the iMac against one another. I wonder if iMac is verbally trademarked by...
Yeah, just say
Mr.
generic
Cook.
computer.
Generic one-piece computer.
Okay. So these are the 2 miners who are competing right now to fingerprint a block, SHA-256 of that block, pick a random nonce, and have the output be less than this target. So what happens?
So both of them guess. Mr. Robot guesses 1, and one-piece computer, purple computer, guesses 7.
Okay, these are the nonces they're guessing.
Yeah, these are the nonces. These are not the outputs. You'll see that the actual pin on the number line is the actual output. So let's say, I don't even want to try and guess how we would pronounce what number came out, but
let's just leave
it's like
it at that.
50% of the number itself, and then Mr. Robot gets like, I don't know, 75%.
Okay, but notice that there's no relationship. Well, actually, you'll see on the next time they guess again.
Yeah.
There's no relationship between this random nonce and the position on the number line. Otherwise, remember, SHA-256 is not supposed to be able to be steered in any way. You shouldn't be able to figure out, oh, if I just change this one number or I change this character, then I'll finally get that.
Yeah.
No, there shouldn't be no trends that you could follow. So green Mr. Robot guy or gal picks 99, and it's closer, but still too high, not below the target. 15 is what purple one-piece computer goes with, and that's much higher. But again, you can't infer any. It's not like you guess and check and you say, oh, I need to guess lower.
Yeah, when I guess this higher nonce, the output is lower. Nope. It's completely unpredictable.
Yes.
So 124 and 0.
Still not there.
63 and 42.
Aha.
Voila. 42 was the answer. So when the one-piece computer, when the purple computer guessed 42, we added that little pin, which is smaller than the target. And that means that the purple computer has found proof of work.
So this is just a super quick visualization of what's happening with 2 miners. Now imagine this number line stretches around the Earth a trillion times. And
Yeah, the number line is way bigger, and the target, that red line, is way closer to the left side.
And there are thousands of miners rather than 2, and they're all trying to guess. And it takes about 10 minutes, if everything goes well, for somebody to get it right.
Yeah.
Welcome back. So in this quick video, we're going to return to this, what do you call this, visualizer, little interactive demo of a simplified blockchain. We have our same transactions in here from, to, and amount. Kevin sent me 10 Bitcoin in this example. Now what we're going to show is what is happening when we click this mine button. So let's not say that I'm malicious. Let's just say that this block hasn't been mined yet. It's still in the process of new transactions are being added in. So Colt, I send Montana, I don't know, 2.3 Bitcoin. Okay, so now what we're looking at is we need miners to compete to take this data, to take the previous hash, which you can see is here from, I think it's, I need to scroll over, but 0.0000221 from here. And I need to take that, and we need to change the nonce over and over and over until we find something. In our case, it needs to start with 4 zeros.
Yeah, so try changing it to 29,267.
Nope. Does not start with any zeros.
Nope.
And you can see I keep changing this. We're not getting close. So when I click this mine button, what the JavaScript on this website is going to do is just try this over and over and over. And it might take a little bit, but this is still much, much simpler than the actual difficulty that we looked at. If you remember, we started with like 20 zeros on the actual blockchain. We're dealing with 4 here. But you'll see, oh, that was fast. Ruining my video here. Come on.
Ruin everything, JavaScript.
Anyway, you can see this is the nonce it picked, and it ended up with this hash.
2.2.
Let's just try one more. See how long it takes. All right, this one's taking a little longer. There we go. Picks a nonce. I tried a bunch of them. This is the one it settled on, and we started with, here we go. We started with 4 zeros. Okay, so hopefully now that makes sense. What is actually happening? Even though this is totally fictitious, just a demonstration, and also much, much faster. It takes one computer a couple seconds max to guess something that has 4 zeros at the beginning. It takes 10,000, give or take, computers guessing millions of times each to...
way more.
It takes
than
them 10 minutes on average to do the same thing.
So if you were to run your computer for an entire year straight, even if you had a real fast computer, it's almost certain, and I can't say impossible, but it's almost impossible to actually find a valid proof of work with just one computer. The Bitcoin network benefits from the amount of people working together and the probability distributed over that many computers attempting in unison.
For the last time, returning to this, remember, a nonce in the real world on the actual blockchain looks something like this, much longer. So it could be 1 or 10 or something small like that. It's just really unlikely. You can see we're at 2.4 billion?
Yeah.
And then what we're guessing, we're trying to find a number with a lot more leading zeros, as you can see here. All right, welcome back. So we've been talking about Hashcash for a little bit now, but we've been skirting around these 2 terms, target and difficulty. We've basically repeatedly said, we'll cover that later. Don't worry about it. That's, some of my previous students know, that's something I probably say too much in my courses. But honestly, in this case, the focus in Hashcash was talking about the basics of the algorithm. That's what we wanted you to understand, this basic challenge. As far as the target itself and how it's calculated, we're going to discuss that in this video and how it relates to something called difficulty. But we'll warn you,
this video is a little bit mathy. So if you don't really care about the math, about how target is calculated based on difficulty, the short answer here is that the target is based on difficulty. And the target is the value under which you want your hash, your fingerprint, to land.
Right.
And when the difficulty goes up, the target will go down. And the Bitcoin network actually adjusts the target based on how quickly miners are finding the answer, finding proof of work.
Right. So remember this example, this number line, this is not to scale because this is a very easy problem in this case. But what we're trying to do, the point of Hashcash, SHA-256 over and over, you change the nonce on a block, and that's the only thing you're altering until you find an output that is less than the target. So the smaller the target, the fewer numbers there are less than that, so the harder it is. So as Kevin is saying, the network updates every 2 or so weeks to reflect...
Every 2016 blocks.
Yeah, which is about 2 weeks, right?
I think it's exactly 2 weeks if they're all on 10 minutes.
Okay, so whatever the period of time is, it's 2016 blocks, and it looks back, the network looks back and says, you know what, I think we were a little fast during that time. Let's slow things down. Let's make it harder. So then they change the network changes itself. It changes the difficulty, which makes the target lower.
And the opposite can also happen. If the network is going too slowly, if blocks are taking too long, then the target will be raised. And how do they do that? By lowering the difficulty. It becomes less difficult for miners.
Okay, so what we're going to do now is talk about the math. So that's really all you need to care about. Is if you want to stop this video, you can. But if you want to learn about the math, learn about the actual numeric values that are assigned and see the current target, see the current difficulty, that's what we're going to do now.
If you're curious.
So there's this equation, target equals n over difficulty. What is that?
And n is a constant, so target is calculated based on n divided by the difficulty.
So n is not actually 16. N is a much, much larger number. It's part of Bitcoin. It's built in. And we'll show you it on the next slide. But the relationship is the same, whatever n is. So imagine we're starting our own cryptocurrency with an n of 16. Remember, Bitcoin's is much larger, but we're saying 16 so that we can do the math easily. And at the very beginning, we set the difficulty to 2.
Yeah, so if we started with 2, we take n, which is 16, and divide it by 2. That gives us 8. So our target lands at 8. Now let's say over the course of 2 weeks, more miners show up, and we want to double the difficulty. Then by taking difficulty from 2 to 4, our equation would then become 16 divided by difficulty of 4, which would give us a target of 4. So what the proportion to notice here is that if we double difficulty, then target gets cut in half. They're inversely proportional.
Yeah. So again, the reason the network does this is not just because it wants to make things harder for no reason. It's that it wants blocks to take a pretty constant amount of time, as much as possible, as close to 10 minutes per block, right?
Yeah, plus or minus a minute or two, but ideally it should be every 10 minutes.
So if some crazy event happened and half the miners just disappeared, I don't know if that could happen potentially, but
maybe
if that
a virus
if that happened, then the network all of a sudden would statistically, it would take a ton longer, twice as long, in order to find the solution for a single block. And then that slows everything down because if we're talking about the same transaction volume, then there's a backlog and things aren't getting processed. So it's important to keep, as much as the network can, to keep a pretty constant amount of time per block. And so that's what's happening here. Difficulty is the way the network regulates that.
So on this slide, we have the real N for Bitcoin, and it's this number. Oof.
No. Okay, nobody pronounces that. It's a very large hexadecimal number. Okay, Kevin, be quiet. So it's a really big number, as you can see here. And it's an hexadecimal because it's just easier for us to fit here. And also it's just a cute little number, all those zeros and Fs. Okay, so if that's what N is, and it's always been that is part of Bitcoin. So instead of 16 divided by the difficulty, we're taking this massive number, dividing by another really large number. This is the current difficulty.
For when we wrote the slide.
Yeah. So actually, why don't we just go take a look really quick at the Blockchain Explorer. So here's the block we've been looking at, 520,091. Actually, I think we were looking at 92. But anyway, scroll down, you can see difficulty. Here we go. 3 trillion, is it? 839 billion. Did I do that right? Yeah, 316 million. Okay, that's the difficulty. So if we compare that to, let's go back in time to like half the number of blocks. Let's go to block, what should we do, 250,000?
Yeah, so this will be about 4 or 5 years ago.
You can see difficulty was only 37 million.
Yeah, so way smaller.
And we're talking about trillion today and million back then. And if we go all the way back, let's go to like block 10. Difficulty 1.
So that means just N was, so the target was exactly N.
So you can see that over time, difficulty has changed, and the trend is that it's gone up, but it doesn't have to always go up. There could be a time where it goes down.
And so for the current difficulty, we actually take that N, we divide it by current difficulty, and it gives us a target of 7.78 times 10 to the 54th power in scientific notation. So That's 7 with 54 zeros in it. It's a very large number. So what it comes down to is just finding a fingerprint of a block given a random nonce that is less than 7 with 54 zeros after it. So for a difficulty of 1, as you saw on block 10, what that means is the target was actually just this number on the left, was n. If you take n divided by 1, the target is itself.
Yeah.
And so early miners just had to have that many leading zeros.
Yeah, whatever that
8
is.
Or 9?
8? I think it's 8. So your number, the result of the fingerprint of SHA-256 had to start with 8 zeros. And today we're looking at, 20 or so zeros?
Yeah, a lot harder. And if you think about this in terms of hexadecimal, if you're taking these as sequences of coin flips, at the beginning, all that a miner had to do was flip 256 coins, and the first 32 had to be heads. But now that we have, say, 20, that means that you need to have 80 heads in a row. And that's a lot less likely.
Okay, so it's a lot of math.
Let's take a breath. We've included this cute little picture of a baby cow. This is a break from the math.
Yeah. So moving on from this cow.
Yeah, back to the math. All right. Here's the number line that we had. And hash cash, as of Q1 2018, is you need to land your fingerprint below this number. So, and we're going to try to depict this number compared to the actual number that it could be, to give you a sense of the scale and the unlikelihood of finding valid proof of work with just a random guess. So in the next slide, this is the real number, 2 to the 256 minus 1. That's the maximum fingerprint that you could produce.
Yeah.
Remembering that a fingerprint is just a very big number, and we represent them with hexadecimal values. So back to 2 to the 256. Now, what we're going to do to simplify this, let's represent the actual target as 2 to an exponent. So it looks a little more similar to the right-hand side. So the target as of 2018 Q1 is about 2 to the 182nd power. Now, this is of course not drawn to scale, and those two numbers don't look so different. But the number 2 to the 182nd power is a lot smaller than 2 to the 256th power. That means you have to take this number on the left and multiply it by 2, and then by 2, and then by 2, and then by 2, about 70 times to get to the maximum value. So it's 2 to the 70th power smaller.
And so this is as close to being accurate as we can get, but this is still not even close.
Yeah, you can see a pixel there, and that's just wrong. The red should be up against the left. So a standard computer to actually do this, it would basically, the statistics we looked up is a MacBook 2014, give or take, can do about 1.8 million hashes every second. So that's 1.8 million guesses in a second. So for a MacBook to actually find proof of work by itself would actually take about 10 million years.
Okay, I am skeptical of that. But
so the reason that's such a massive number, and the reason that the difficulty has gotten so high, is because MacBooks are no longer miners. The new mining hardware is specialized chips called ASICs, application-specific integrated circuits. And these are microchips that have one job and are good at doing only one thing, and that's calculating fingerprints. So you give them a number, and it gives you the fingerprint very quickly, much faster. Thousands, sometimes millions of times faster than a normal computer can do it. And that's what makes this problem tenable. But this is also a frustration for a lot of people with the Bitcoin network, is that you can no longer use general purpose hardware to participate on the Bitcoin network. It's so difficult to mine now that it's really become a situation, these chips are an economy of scale. So that's why there are these cartels, people who have invested a lot of money into massive mining operations that are running really the big show.
So here's a simple example of, this is a very low difficulty example where the target is a very high number relative to the current targets that we're looking at.
And then the left is a fingerprint.
Yeah, so how many zeros are we looking at here?
I think this is 9.
Okay, 9 or 10
10.
fingers. Gosh, 9 or 10 zeros.
10 fingers.
So basically all that you're trying to do, if this is the target, and maybe this was the target a couple of years ago, for example, you're trying to find a number the result of SHA-256 such that it is less than this. So for example, we just focus on the first digit there. All the zeros need to be the same, and then the first digit needs to be smaller.
Yeah.
Or, I mean, this whole thing could be zeros, and it would satisfy the requirements. It's just really rare to get. Sometimes on the blockchain, you will see something that has an extra zero, or maybe even more, but it's just really hard statistically to actually find that.
Yeah, it tends not to happen.
So here's a block. This one is 250,002. This was back, when was this? 2013. Okay. So all that we'll say, you can see here, we've got a bunch of zeros. We're not going to count them out, but there's a bunch of zeros. Remember, the target itself is not part of the block. It is calculated based off of the difficulty. So the difficulty is here, but nowhere on the block does it say the target is exactly this.
Yeah, miners calculate that, and people verifying the block calculate that on their own.
But this is the hash that was found. The correct nonce, or a correct nonce, this large number down here.
Mm-hmm.
So when you take this, hash it with everything else, SHA-256, this was an output with however many number of zeros in there. That made it less than the target.
And same as the case for the previous block, same as the case for the next block. And that's why you'll see in a lot of our slides and then on a lot of these, like block explorers, you'll see a bunch of hashes that begin with a bunch of zeros. And that's because these are small fingerprints.
Okay. All right. Welcome back. So continuing on with Hashcash, just a little bit more. You might be sick of it, I know, but it's really important. So what we're going to do is actually walk through a really, really simplified, basic example, but a real example. So rather than working with SHA-256, where the output looks something like this, so instead, we're working with SHA-4, a much simpler version. And just to clarify, SHA-4, this is confusing.
It's not like SHA-2 or SHA-3. We've gone and made it
Those are
more
the
confusing.
families, the general families, SHA-2 and SHA-3. SHA-4 is not used by anybody, but we're just making it up. And it's the same idea, except the output is 4 bits. So
instead of 256 bits, it's just 4 bits.
Yeah, so an output might look like 1011 or 0001. But when we put that in hexadecimal, which is what these are in, we're talking about a single digit because there are 16 options. So 4 bits means there's 16 possible numbers we could represent from 0 up to 15. So when we do hexadecimal, that means 0 up to the letter F. If none of that makes sense, it doesn't really matter. All that we're trying to do is hash this together, and our output is going to be some number between 0 and 15. And we're trying to find an output that's less than our target, which for now is 2. So we're using 2. That's our example.
Yeah, so we're still going with an N of 16. So difficulty 8 would give us target of 2.
So what we need to do is find a nonce, continue to pick a random number, hash this thing together until we get an output from the fingerprint that is less than 2.
So on a number line, it's going to look like this. So if we're rolling a die, and we're trying to land it between 0 and 15, then a 0 or a 1 will count.
Yeah.
We're considering this less than, not less than or equal to, so 0 or 1 are what we're looking for.
And this is a super easy one. Obviously, it wouldn't take very long.
So we pass 87
as the nonce,
and our fingerprint, our SHA-4 fingerprint, is the number 13.
That's too high.
Yes, too high. We're giving you the decimal version because hexadecimal is a little more difficult for most people to read.
Yeah, so we need to find a number less than 2. So we need to change the nonce.
So guess again. 6, we get 9. 13, we get 2.
Still too high.
26, we get 5.
42,
voila, we get 1. So what we've just done is we've established proof of work on this block. We've found a random number by looking through a bunch of guesses that when hashed with this block produces an output, a fingerprint that is less than our target.
Oh, so, Kevin, we forgot. We have.
Oh, my effect.
There we go.
Love that. So this is a valid proof of work for this block.
Yes.
And this miner would then win the block with the Bitcoin associated with it.
Which in the next video, we're talking about rewards. So
Yeah.
jumping the gun a little bit. But as you can see, this is a very simple example, but we change the nonce, we get a different output. There's no pattern that we can follow. We couldn't have just said, 87. Okay, that's too high. We got 13, so we need to do lower. We go down to 6, then we get 9. We go to 13, then it goes down to 2. We go to 26. There's no pattern that we can actually follow here. And 42 is what eventually gave us 1. And this is one potential solution. There's not only one answer, remember. It's just about finding an answer that works. The other thing is that, of course, this is much, much easier than the real version of this. So in the real world, in Bitcoin, it's way, way more complicated and harder to do. It involves way more guesses. We actually have some stats on this.
So this is what the network was running at earlier this year when I calculated this. This is 10 million terahashes per second.
Wait. What's a terahash?
A terahash is 1 trillion hashes per second.
Okay, so that's just 1 second. We're doing a trillion guesses, but it still takes how long on average? It takes
10 minutes.
10 minutes. So let me go back to the stats here.
So it's 10 quintillion guesses a second. And at 10 minutes, it's 6 sextillion guesses, which is an unimaginably large number.
Yeah, so this is the number of guesses, on average at least, that it takes. Yeah. Remember, it could be the very first guess that a miner makes.
It could.
It's just really, really unlikely that happens, but it's possible.
It's just by the law of large numbers that this tends to happen after about 6 sextillion guesses.
So in summary, it takes a lot of guesses, a ton, 6 sextillion guesses on average. Huge number in the real world with Bitcoin compared to what was ours, like 5 guesses or something until we got it right.
Yeah.
But that's what you get. That's the idea, is that it's supposed to be hard. It's supposed to involve work. Remember, it's all about deliberately slowing down the network and making it so that it takes time, it takes effort in order for a new block to be mined, and it's not instantaneous.
And that's 6 sextillion. In the last chapter, in the last video, we mentioned 10 million years for a MacBook to guess this. It would take about 10 million years for a MacBook to make 6 sextillion guesses.
Yeah, so that's just one MacBook we're talking about. The network, it doesn't really consist of any. Well, I guess there are MacBooks on there.
There's probably a couple.
But the majority of the miners who are winning, who are correctly mining things, are farms of ASICs,
mining machines. Yeah,
anyway.
Things specifically for this.
Okay.